Alrighty, howdy folks. We will look at chapter 11. So we are starting a completely new chapter, section 11.1, and this is about sequences. Let me tell you something. When it comes to calculus 2, in my opinion, if you learn integration, starting with that 5.5 substitution rule and all of the stuff in chapter 7, all the integrals, and then this chapter, sequences and series. If you master these things, that's it. That's the most that you need to learn. Of course, there are other topics, but they are all, in my opinion, slightly less important. Okay, so focus really well on chapter 11 as well, and we'll be done. Okay, sequences. Mathematicians always do this. The moment they start something, sequences, they start with, what's the definition? So let me start with the definition. A sequence is a list of numbers written in a specific order. And typically we write sequence and put in curly braces a sub n. When we denote something like that, what we actually mean is, oh, that's the same thing as saying a sub 1, comma, a sub 2, comma, a sub 3, and so on up to a sub n, comma, dot, dot, dot. And what is interesting to note in all of this is a few things. A1 is the first term. What is that? Some number. 5. A sub 2 is another number, the second term, the third term, and so on. And a sub n is the nth term of the sequence. Okay. But then, up until high school, you did see, I mean, it's not like you didn't see sequences before. In high school, when you saw sequences, what you saw was only things that went from A1 through AN. It terminated right there, which means you looked at only finite sequences. I'm sure you must have even learned formulas. Hey, boys and girls, did you know 1 plus 2 plus 3 plus dot 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 plus n is equal to n times n plus 1 over 2? Right? So I'm sure some ACT, SAT tests you must have had. Find the sum of 1 plus 2 plus 3 plus dot 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 100. And you just apply that formula, n times n plus 1 over 2, and you got it. But notice in there you are dealing with finite sequences and series. Series is nothing but you add up all these terms. I'm sorry. But here, now that we are in college and in calculus 2, we are big boys and big girls now. So we deal with infinite sequences. Cool? And that's why you see a sub n, comma, dot, 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 telling you that that sequence is going to continue on forever and ever and ever. Okay? And so where a sub 1 is this, and the generic nth term of the sequence. There are other ways of denoting the sequence. You can write a sub 1, a2 also as simply curly braces a sub n, or curly brace a sub n with n equals 1 to infinity, like that. So these are other notations. I just want you to be familiar with that. Note the 3 different forms of indicating the same sequence. If I said this, right, you should understand that's a sequence, right, where n equals 1 to infinity, going from, and we have n plus 1 over n plus 2. Or I could say this is a sequence with a sub n equals n plus 1 over n plus 2. Automatically you should understand that the index of the sequence is 1 to infinity. Okay, and or I could just expand everything out and say, when n equals 1, we have 1 plus 1 over 1 plus 2, that is 2/3. N equals 2 gives you 3/4, and so on. So there are three different ways of saying the same sequence. Or I have another example here, and which we can write like that. Okay. And with that, let's look at some simple problems. List the first four terms of the sequence a sub n equals 1 over n minus 1 factorial. You have some problems like this in the book. Is that simple enough? I think so. Given a sub n to be this, can we figure out a sub 1? What is the value of n? 1. Yep. How do you find a sub 1? Plug n equals 1 into the expression on the right hand side. So we have a sub 1 is 1 over 1 minus 1 factorial. 1 minus 1 is 0. 0 factorial. What? 0 factorial. 0 factorial by definition is actually equal to 1. So we have 1 over 1 is equal to 1. So I know you might have been tempted to go, hey, how come you were dividing by 0 and you said that's equal to 1? No, 0 factorial is actually 1. Okay. A sub 2, plug n equals 2 and you get 1 over 1 factorial. 1 factorial is just 1. And a sub 3 is 1 over 2 factorial. 2 factorial. Wait a minute. What in the world is factorial? I hope you know what factorial is, right? Factorial, maybe I'll quickly define. N factorial is nothing but n times n minus 1 times n minus 2 times ... 3 times 2 times 1. Okay, so if I want 5 factorial, I start with 5 and I keep multiplying. Start with a 5 times. 1 less than 5 is 4. 1 less than 5 is 4. So 5 times 4. 1 less than 4 is 3. 2, 1. So 5 times 4 times 3 times 2 times 1. That is what 5 factorial is. You get the idea now? Okay. So 2 factorial is start multiplying. Start with a 2. The next term is 2 times 1. That's it. When you get to 1, you stop. 3 factorial is 3 times 2 times 1. We reached 1, so stop multiplying. And so this is the idea. This is how you list terms of a sequence. And list the first 6 terms of the Fibonacci sequence. There's an interesting sequence called the Fibonacci sequence. And here is how it is stated. A sub 1 is 1, the first term of the sequence. Second term is also 1. And when it comes to evaluating the subsequent terms, you have a formula. A sub n is a sub n minus 2 plus a sub n minus 1. Meaning, maybe I will show. So a sub 3, according to this, should be what? A sub 3, n is 3, should be a sub 3 minus 2, which is a sub 1, plus a sub 3 minus 1 is 2, so a sub 2. Basically, a sub 3 is a sub 1 plus a sub 2. Would you agree? And what is a sub 1? 1. What is a sub 2? Is also 1. So a sub 3 is a sub 1 plus a sub 2, and that turns out to be 2. Fourth term, a sub 4. Go back to this formula, plug n equals 4. You get a sub 4 minus 2 is a sub 2. 4 minus 1 is 3, so a sub 3. A sub 2 plus a sub 3. Do we know a sub 2 and a sub 3? Yes, we do. A2 is 1, a sub 3 is 2, so 1 plus 2. And so on. Fifth is a sub 3 plus a sub 4. Sixth is a sub 4 plus a sub 5. And so the Fibonacci sequence is 1, 1, 2, 3, 5, 8, 13. Yikes, 13 plus 8 is 21, and so on. And it's a very interesting sequence. Somebody said, what if we were to make squares of Fibonacci sequence and put it this way, and arrange them this way. So I don't know, you can see this itty bitty square of size 1, and this is also another square 1, so that's first and the second terms, and below that is a square of the other Fibonacci number, the third Fibonacci number 2, and there's a 3 and a size 5, size 8, size 13. So you have squares like this, and then there's a particular scheme that you use as you draw this curve. You draw a curve between that point and the second or the third square, the bottom point, and the fourth square, and the fifth square, sixth, like this, and you get this spiral. Cool? Yeah, what's the big deal about that stupid spiral, man? There's a big deal about that spiral is a lot of things in nature actually display that spiral. When you look at the seeds in a sunflower, they are arranged in this particular pattern. Apparently, that is the most optimal way of arranging things. Sunflower seeds. And you see, I don't know what this is. So there's another one. And this is the Nautilus shell. Look at the shape of the outside curve. Exactly like this guy. Even galaxies, spiral galaxies, tend to have this particular shape. Okay. The DNA helix is like that. And some of the cyclones. I say cyclone. Hurricane. Cyclone is such an Indian term. Hurricanes, they have the same shape. Okay, so all of this stuff is not just some stupid thing for mathematicians to torture you with. There are wonderfully practical things that follow these things. Okay, with that, let's move on to arithmetic sequence. What's an arithmetic sequence? An arithmetic is a form a, comma a plus d, comma a plus 2d, and a plus 3d, and so on. Basically, what is it? You start with a number and you keep adding the same number. Okay, a plus d. Then to a plus d itself, you add another d, which becomes a plus 2d, right? And so on. So that is an arithmetic sequence. Now, let me ask you, what is the first term of this arithmetic sequence that I have shown you? First term, a. Good. What's the second term? A plus d. Third term, a plus 2d. What is the nth term of this sequence? Can you figure that out? Look at the pattern. Let me start with the third term. A third term has a plus 2d. Notice how I'm phrasing it. The third term, insisting on third, has a plus 2d. Third has a 2. Fourth has a 3. Fifth has a 4. Nth has a n minus 1. So basically, nth term would be a plus the quantity n minus 1 times d. Cool? So the nth term of an arithmetic sequence is this, where a is the first term and d is called the common difference. And you need to know this one. You definitely need to memorize that. Nth term of an arithmetic sequence, a plus d, a plus 2d is a plus n minus 1 times d, a plus the quantity n minus 1 times d. Similarly, there is something called a geometric sequence. A geometric sequence is of the form AR square, AR cube, and so on. You start with a number called A. To get the second number, multiply the previous one, which is A, by an R. You get AR. Now AR itself, multiply that by an R, and you get the next one, AR square. And to get the next one, multiply this present one, AR square, by an R, and you get the next one, AR cube. So each time you're multiplying by an R. Naturally, I want to ask you, what is the nth term of this sequence? You see a pattern? Again, I think I'll start with the third one. Third has a 2 in it. Fourth has a 3 in it. Nth has a n minus 1 in it. AR to the n minus 1 is the nth term of a geometric sequence like this. A is the first term and R is the common ratio. Cool? All right. Now, I needed to talk about all of that because I want to ask you a few questions. Let's solve a few problems, in fact. What is the a sub n, the nth term of this sequence? Assume that the pattern continues. 1, 1/4, 1/7, 1/10, 1/13, and so on, is the question. To me, whenever I look at something like this, I look at it this way. Are the tops always 1? Yep. So clearly, our a sub n, the top will be 1, the numerator. Okay, what are the denominators now? In the first term, what's the denominator? There's no denominator, man. Yeah, so 1 is the denominator, right? 1 over 1. So the denominators, when you look at them, you have 1, 4, 7, 10, 13, and so on. Do they follow a pattern? 1, 4, 7, 10, 13. Do they look like any sequence that we just discussed? Yeah, man, that's an arithmetic sequence. You got, you recognize this? Then you're good. So the denominator is 1. The first term of that arithmetic sequence is 1. And you're adding what? 3 each time. Oh, so the common difference D is 3. What's the nth term of an arithmetic sequence? What's the formula? A plus the quantity n minus 1 times D. So A is 1 plus the quantity n minus 1 times D is 3. So this is 1 plus 3n minus 3, which is nothing but 3n minus 2. Right? So we have a sub n is equal to 1 over 3n minus 2. And what's with this n? All I'm just saying is n is a natural number. N is an element of natural number set. N is in the natural element set. Natural number set. That means n takes on values of 1, 2, 3, 4, and so on. Cool? So we have the nth term of this sequence figured out. Let's do a few more. What about this? It's the same problem, man. No, not quite. What's the difference? The top is positive 1, negative 1, positive 1, negative 1. So the top is alternating between positive 1 and negative 1. Okay. If that is the case, how do we account for it? We account for it by saying, no big deal. Let's call it negative 1 to the n minus 1. The only thing you have to think about is whether you should call it negative 1 to the n or negative 1 to the n minus 1. So in this case, if n is 1, the first term, We get negative 1 to the 1 minus 1. 1 minus 1 is 0. Negative 1 raised to 0. That is positive 1. Right? Is the first term positive? Yep. So this checks out. Cool. Let's check another one. Let's look at what this one says the second term would be. So n is 2. Plug n equals 2. You get negative 1 raised to 2 minus 1 is 1. So negative 1 raised to 1 is negative 1. Is the second term negative? Yep, it is negative. So what we have is perfectly fine. Cool? All right, let's go to another problem. 5 half, 9 6, 13, 18, 7. So what's with this guy? Let's try to isolate the tops and the bottoms. Okay, let's look at just the tops alone. 5, 9, 13, 17. Hey, that is an arithmetic sequence, right? Each time we are adding 4. Cool. Apply the a plus n minus 1 times d to this and you get the top. What's with the bottom? 2, 6, 18, 54. Any thoughts? Hey, that's a geometric sequence. We are multiplying by a 3 each time. Good. So when you do that, when you apply all of that, a plus n minus 1 times d to the top, trust me, when you simplify, you get 4n plus 1. And we say the bottom is a times r to the n minus 1, 2 times, a is the first term is 2 for the denominators, times r to the n minus 1. Cool? So that's how we figure out the nth term for this problem. Yeah. What about this? 1 0 negative 1 0 1 0 negative 1 0. See any pattern? Well, it turns out this is sine of n pi over 2. What? Yep. Let's see. The first term should turn out to be 1. Does it? Plug n equals 1. You get sine of pi over 2. What is sine pi halves? 1. Yep, that worked out. When n equals 2, the second term, n equals 2 makes this sine of pi. Sine pi, is that 0? Yep. Sine of 3 pi over 2. Negative 1? Yep, that checked out. Sine of 4 pi over 2 is sine of 2 pi. Hey, that's also 0. Cool. So, this is correct. Alright. Alrighty. Let me discard that. Let me go to the next slide. And whoa. And talk about how long was that in? 23 minutes. Okay. I can start with the next one. So we are continuing with the sequences, and there's some concept that I want to show you here. Okay. We need to recap the concept of limit of f of x as x approaches infinity, which we studied in Calc 1. Okay. Have you seen a graph like this? Does it? Can I ask you? Hey, look at this graph of some y equals f of x. Now, what is limit of f of x as x approaches infinity? If I were to say, what would you say? As x is getting bigger and bigger, the y values are approaching 1. Though the limit of f of x as x approaches infinity equals 1, man. Yes, you're right. You're absolutely right. What do you call that line, y equals 1, the dotted line? It's called the horizontal asymptote, right? Ah, so can you define a horizontal asymptote? Oh, horizontal asymptote is as simple as this. The graph approaches that asymptote but never crosses it. Is that what you said? The graph approaches the asymptote but never crosses it. If you said that, let me ask you. Could the graph have looked like this? What would you say limit of f of x as x approaches infinity is in this case? Still 1. Uh-oh. The graph does cut that horizontal asymptote. Right? Okay, Dr. Sam, I got it, man. The thing is, the graph may cut that horizontal asymptote, like, for small values of x. In the beginning, it may cut. But, like, if you go far and far away, there it won't cut it. Is that the modification that you want to make? Maybe. And you think you're being very clever. Aha, gotcha. Right? You know how I know that? Because I used to say the same kind of nonsense. And I felt like, dang, look at how smart I am. And then somebody said, nah, what about this? What? I was like, damn, you mathematicians. You're way too clever, man. Now what would we say? Is limit of f of x as x approaches infinity, is that still equal to 1? Yep, it is. Is the graph still cutting as x keeps on increasing? Yep. But yeah, I know. So if you can zoom in, this graph is cutting that horizontal asymptote forever and ever and ever. Right? The thing is, when you are in pre-calculus, you learn about asymptotes, horizontal asymptotes. There, you cannot be taught about what exactly is a horizontal asymptote because you don't know the concept of a limit. And that is the issue. However, now that you know what limits are, we can be a little more sophisticated in our way of talking about this. All right. So let's recap as to what the... this is the reason. No. The reason I wanted to show you all of that is, once we get a precise definition of a limit as limit at infinity, we can have a much better understanding. So here, look at this. The limit at infinity, limit of f of x as x approaches infinity equals L, if for every epsilon, which is a positive number, there exists an n such that x is greater than or equal to n implies absolute value of f of x minus L must be less than epsilon. Right? Simple, straightforward, clear as mud. What the hell did you just talk about, man? Well, what that is saying is, suppose you are claiming that limit of f of x as x approaches infinity is equal to L. Okay, that's your claim. Then for every epsilon, as long as you pick epsilon to be positive, which means I can pick epsilon to be 1, 2, 0.1, 0.01, 0.0001. So I can pick any epsilon as long as it's a positive quantity. For that, you, who is claiming the limit to be L, you must find an uppercase N. Okay? Okay, what do you mean some uppercase n? Yeah, some uppercase n. What should that n satisfy? Please look at the bottom one. They are both the same, but the bottom one is a little more easy to understand. You must pick an n such that if I were to pick x greater than or equal to your n that you picked, the f of x value must lie between L minus epsilon and L plus epsilon. That must happen. For any epsilon I pick, you must show me that there is an n such that f of x will lie between L minus epsilon and L plus epsilon whenever I pick x to be greater than or equal to n. Now I know. Still not so clear, man. I'll show you with an example here. Graphically. Okay. Now notice what am I asking you to observe here? This is the graph of 1 over x. All right. So that black line is the graph of 1 over x. Looking at it, would you say limit of f of x as x approaches infinity is 0? Limit of 1 over x as x approaches infinity is 0. Oh, okay. So L is what? L is 0 here. Now, what did I say? For every epsilon, you must pick an uppercase n that satisfies some particular condition, right? So if I were to pick epsilon to be, say, here I have 0.2. Okay, let me pick epsilon to be 0.2. This one says L minus epsilon and L plus epsilon. A sub n or f of x should lie between L minus epsilon and L plus epsilon. L is 0, 0 minus 0.2, epsilon is 0.2, and 0 plus 0.2. So you notice when I say L minus epsilon and L plus epsilon, I mean the green lines. The bottom green line and the top green line. Now, are all the f of x values lying inside the green band for a particular uppercase n? Yeah, if I were to pick uppercase n to be 5, if I pick any x greater than this 5, the corresponding y values are lying within that green band. Isn't that the case? If I pick 6, x to be 6, look at the corresponding f of x value. Oh, that dot is certainly in between this green band. Similarly, for x equals 7, x equals 8, for every value of x greater than 5, we notice that f of x values lie within the green band. So, I have shown you that to be the case. Now let me ask you, what if I were to pick epsilon to be 0.1? Now, L minus epsilon becomes 0 minus 0.1 is negative 0.1, and we have positive 0.1. So that is the blue one is the band. The blue lines indicate the band in which your f of x values must lie. So, can you figure out what an uppercase n ought to be? Any uppercase n, which satisfies the condition? Can I pick uppercase n to be, say, 3? No. If you say uppercase n is 3, and if I pick x to be 4, that y value is not within the blue band. So no. That n is wrong. Okay, let's see. Could you pick uppercase n to be 15? Okay, let's see. If I pick x to be greater than 15, that is, say, 16, is the y value within the blue band? Yep. Okay. How about 17? Yup. 18. Huh. So you could pick for uppercase N a value of 15. That's okay. But in fact, perhaps you could have picked N to be uppercase N to be 10. Even that would have satisfied. Ah, cool. That's the idea. Right? So this is a more precise definition of limit at infinity. Now, obviously, the question is, what does this got to do with sequences, man? Well, let me go back. Boy, did I confuse you? If you didn't get all this theoretical part of it crystal clear, don't worry too much about it. But if you do, it's more power to you. All right. Maybe I should have said that in the beginning itself. I'm going to discuss a little bit of a theory here and see if it interests you or not. Okay. Would you agree that we can think about a sequence called 1 over n? Sequence 1 over n? Yeah. Can you tell me the terms of that sequence? N equals 1 means 1 over 1 is 1. 1 half, 1/3, 1/4, 1/5, and so on, right? Oh, that sequence. What has that sequence got to do with a function called 1 over x? It's got everything to do with that function. What's the difference between the sequence 1 over n and the function 1 over x? Graphically, the solid line, the solid curve that you see is the graph of 1 over x. Whereas the sequence is only those dots, 1 over 1, 1 half, 1/3, 1/4, 1/5, and so on. So, the whole idea is, can we talk about the concept of limit of f of x as x approaches infinity? Yeah, we can. Can we extend that to the concept of limit of a sequence? That is the key. Yeah, if we can say what is limit of 1 over x as x approaches infinity, we can easily say what is limit of a sub n as n approaches infinity. What's the difference? One is a solid curve, and the other one is just a bunch of dots. But the dots fall right on top of the curve. That's the key. I'm going to make one more very important statement. Please pay attention. So, whatever is the limit of the continuous function is the limit of the sequence as well, as x approaches infinity or n approaches infinity.
I'm sorry, cool? But I can only shop in the primary language associated with your Amazon account. If you'd like to switch languages,
Alexa, stop.
Go to set.
I don't know, man. So, where was I? If we know the limit of the function f of x as x approaches infinity, the corresponding sequence also has exactly the same limit. And that is why I needed to talk about all of this. And we're going to apply that concept to a whole bunch of things. Limits of rational functions. What's the limit of a polynomial over a polynomial? What is a rational function? A rational function is a ratio of polynomial over a ratio of two polynomials. So on the top, I have p sub n x to the n plus p sub n minus 1 x to the n minus 1 and so on, plus p sub 0. What is that? What are p sub n? It's like this. It's like 3x cubed plus 2x squared plus x plus 1. Right? Is that a polynomial? Yes, it is. So it's kind of like that. But in the bottom, I have a different polynomial. Q sub m. This is also a polynomial. The top is an nth degree polynomial, and the bottom is an mth degree polynomial. Okay, so the question is, did I say, I shouldn't say n approaches infinity, I'm sorry. It should be x approaches infinity. What's the limit as x approaches infinity of this rational function? Is the idea. And this you learned in pre-calculus. It depends on what the degrees of the top and the bottom polynomial are. If they have the same degree, m equals n, then the limit is equal to the ratio of the leading coefficients. Meaning the highest power is n on the top, its coefficient is p sub n. And the highest in the bottom is q sub m. Right? So p sub n over q sub m is the limit as x approaches infinity. On the other hand, if we have m to be greater than n, the degree of the bottom is bigger than that of n, then that's going to go to 0. Whereas if the top has a higher degree than the bottom, then it's going to be either positive infinity or negative infinity depending on the sign of p sub n and q sub m. Okay, all right. Let me apply that to a few problems and show you. Does it look like a rational function? Is a polynomial over polynomial? Hey, wait a minute. Hey, you were talking about continuous functions, man. What's with this? See? Once we understand concepts from pre-calculus and calculus about limits as x approaches infinity, we can apply all those concepts even to the limit of a sequence like this. What is limit of a sub n? Same concept applies as long as you recognize that a sequence is a bunch of dots that fall on right on top of this continuous function. There is a function called 3x cubed plus 2x squared plus 100 over 4x cubed minus 8x minus 1. So if you look at that graph and look at these sequence, the sequence is just a bunch of dots on that graph. So whatever is the limit of the continuous function is the limit of this sequence as well. So we can apply all those concepts. That's the whole thing I'm trying to drive at. Okay, so do we have the same degree polynomial on top and bottom? So what should this be? Ratio of leading coefficients, 3 over 4. That was the whole idea I'm trying to drive at. Okay, there's another method. What if we divide by the highest power? That is, n cube is the highest power. So let's divide both the top and the bottom by that. Can we write like this? Yup. Now, what happens to the quantity 2 over n as n approaches infinity? Oh, that goes to 0. What happens to 100 over n cubed? That also goes to 0. This goes to 0. This goes to 0. All we would be left with is 3 over 4. That's second method. But there's a third method. I like this one. This one says, because we are talking about, please pay attention, because we are talking about n approaching infinity only in those kinds of cases, you can ignore the lower order terms in favor of the higher order term, highest order term. What does that mean? The 3n cube has an order of 3, right? 3n cube. So 2n square and 100, they are lower order terms compared to 3n cube. So you can just completely drop them, ignore them. Similarly, in the bottom, you can ignore minus 8n minus 1 in favor of 4n cube. Keep the 4n cube, but just completely drop these other two guys. And so you end up with this. Okay. Pay attention to one thing. I am not saying 3n cube plus 2n square plus 100 over blah 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 is equal to 3n cube over 4n cube. That's not what I'm saying. All I'm saying is the limit of this is equal to the limit of that. So those are two completely different claims. Okay. All right. So we have 3n cube over 4n cube. Now n cubes cancel. Limit of that would be 3/4. That's the idea. And I like this method a lot better. First method says, oh, the degree of the bottom is bigger, so that must be 0. If we divide both the top and the bottom by method 2, divide the top and the bottom by the highest term n cube, then we end up with 0 over 4, which is 0. Or the method that I prefer, ignore the lower order terms, and so this becomes limit as n approaches infinity of, just retain the 3n square and retain the 4n cube in the bottom, and so that turns out to be 3 over 4n, right, when we reduce it. Oh, that clearly goes to 0, because in the numerator remains 3 and the denominator goes to infinity. So you have a finite number being divided by a very large number, that is 0. Okay, this one. I like this. Here, notice, we do not have a polynomial over polynomial. The top is not a polynomial, right? It's a radical. So how do we deal with something like this? Well, while strictly speaking it is not a polynomial, we can approach it sort of like it is a polynomial. In other words, method 3, ignore the lower order terms, I said, right? Because we are talking about taking limit as n approaches infinity. So ignore 2. Keep that 9n to the 6, of course, under the radical. Similarly, from the bottom, ignore the 1. And so the limit of this is equal to limit of this. Now that reduces to 3n cube. So we have 3n cube over 4n, and the limit of that is clearly infinity. See, that's the way you solve this problem. Okay, now what's limit of 2 to the n as n approaches infinity? 2 square, 4, 2 cube, 8, 16, 32. Whoa, that's getting big really fast. There's no doubt about it. That limit is equal to infinity. Right? Cool. What's limit of -2, the quantity raised to n? Let's see. -2, the quantity square is +4, -8, +16, -32. So like that, shifting between positive and negative. Right? So what would you say the limit is as n approaches infinity? Careful. So as n gets bigger and bigger, what are the terms doing? They are oscillating between negative infinity and positive infinity. One time it is for a certain value of n, the quantity is at negative infinity. The very next value of n, it jumps all the way to positive infinity. Damn, that would be one heck of a ride, going from negative infinity to positive infinity in just one jump, right? But anyway, what's of interest to us? As a limit, what would you say that is? The limit does not exist, right? Because you cannot have things jumping up from positive infinity to any two numbers, two different numbers. Limit does not exist. Okay, what about limit of 1/2 to the n? That is clearly 0. Because we are looking at 1/2, 1/4, 1/8, 1/16, 1/32, 1/64, 1/128, and so on. Oh, the numbers are definitely getting smaller and smaller. So as a limit, that must equal 0. What's up with the -1/2 to the n? negative 1/2, positive 1/4, negative 1/8, positive 1/16. Surely oscillating between negative and positive. But as n gets bigger and bigger, what would they be oscillating about? About the same number 0. Unlike the oscillation between two different numbers, negative infinity and positive infinity, here we are talking about oscillating about 0, the same number. So guess what? This is actually 0. Ooh, right? Well, pay attention to that. And graphically, if I can show you, this is how the dots look like. The negative 1/2 to the n here jumps up to the positive, jumps down to the negative, up, down, up, down, up, down, but they're oscillating about 0. So the limit of this is in fact equal to 0. Okay. Then what about negative 1 to the n? Negative 1 to the n oscillates between negative 1 and positive 1, jumps back to negative 1, back to positive 1. So when it does that, what can you say about limit of negative 1 to the n? Does not exist, because the numbers are not oscillating about the same point, same value. So limit of negative 1 to the n does not exist. What about limit of 1 to the n? What does that sequence look like? 1, 1, 1, 1, 1, 1. What's that limit? That's 1. So I've combined all of that and I've given you this. Limit of r to the n as n approaches infinity is infinity if r is greater than 1, 1 if r equals 1, 0 if absolute value of r is less than 1, and does not exist if r is less than or equal to negative 1. Okay. This you must remember, please. I think that's a good stopping point for today. Whew. The theory that I explained, I did the best I possibly could. Okay. If it turns out that you didn't understand it that clearly, don't worry about it much. Okay. That's all I can say.